Let's get started, shall we? So let's go back and review everything that we've covered in this section, because we're going to be using that for quite a while now. So remember that we have defined Hilbert spaces. So can anyone remind me what the Hilbert space is? Okay, very good. So we started with vectors, right? X and this x vector, right? And the basis vectors, e's, right? So x could be, for example, we said x1, x2, x3, and so on, right? Up to xp. And E was E1 through EP, the corresponding bases, right, that define our space, and that defines our space here, right? So this should be EI, EJ, EK, and so on. Now, this set, or a set, rather, of vectors X defines a vector space if what two things happen? What two properties?
Addition is defined and closed. Vector scaling is defined.
Okay, so very good. This, scaling and addition are defined and closed, right? Meaning that the result has to be in the set. Okay. Very good. The same applies, remember, to matrices, right? And therefore, the same applies to tensors. We have also defined norms. A norm is a functional mapping, okay? Remember, a norm, a functional mapping that abides by 4 rules, which are, anyone? Non-negativity. So the functional mapping, right? If I call that functional mapping f of x has to always be larger or equal than 0. When is it equal to 0? When x is 0. And it has another property, third property, which is what? Scaling. So if I multiply by this alpha x, this is the absolute value of alpha times f of x. And one more. Triangular inequality, very good, which says that if I do a plus b, that has to be smaller than f of a plus f of b. Okay. Also, we mentioned quasi norms, which satisfy all of these properties except the last one, which it satisfies, but up to scale. Good, excellent. The inner product we define as x transpose y, or x, this star to represent the complex conjugate, right? Y if I'm in the complex domain. Remember that I'm going to be using sometimes this notation, sometimes this other notation, okay, to represent the inner product in the complex domain. And a Hilbert space is a vector space. This is a vector space, right? A Hilbert space is a vector space whose norm is given by an inner product, okay? And there are some other details that are not relevant here, but note that there are other details that I did not include. Okay. We also talk about orthogonal basis. So orthogonal are given when the bases in my space, like the one that I've drawn here, have an inner product, right? EI transpose EJ, inner product, is equal to 0. Okay, good. Now, if EI transpose EI is equal to 1, then they are orthonormal, right? Very good. And because each vector x now, right here, right? So this vector, remember, this is the standard notation that we use, but in fact, a vector is rather given or should be written instead more formally or more completely. It should be written as x is equal to x1 e1 plus all the way to xp ep, right? That's how it should be written. So what I'm going to do, I'm going to write here that x, it's a linear combination, right, over all I of ci ei, where ci's are my coefficients. And these coefficients we showed in our last lecture, they're nothing else than x transpose ei divided by ei transpose ei. Right? Okay, excellent. We covered tensors as well in detail, but I'm going to jump ahead now and extend this not to tensors, but rather to continuous functions, okay? So the same, everything that we have seen in this class, right, in the last few lectures, everything that I've just summarized here on this side of the whiteboard applies to functions as well. Okay? So I can define functional spaces in the same way that I define vector spaces. So in that case, we're going to define the set of functions f sub I. So let f sub I, that set, be the basis set of a space F. Then any function g, right? So f sub i's are the basis functions in the same way that e sub i's here were the basis vectors. Okay? Or remember when we were talking about matrices that we had basis matrices and basis tensors, right, of any dimension or order. So here I'm substituting these for functions. And therefore, any function g, in the same way that any vector x here could be represented as a linear combination of, rather here, as a linear combination of the bases, any function g can be written as a linear combination of these basis functions. So I have g is equal to the sum of some coefficients ci times my basis functions fi's, right? Now note on both sides of the whiteboard that they're exactly the same equations, right? I didn't change anything, but on one side ei's are vectors, and on the other side fi's are vectors. On the one side x is a vector, the other side g is a function. Okay? which means, right, hence, this means that I can now represent a function g, right? I can represent the function g using a standard notation in the same way I represented the vector. Now remember, this is just a convention, right? It's a representation of a vector. This is the real vector. But this is just our convention. Well, we can define the same convention here, right? And I can define g as my vector C1 through Cn, let's say, if I have n basis functions. Now this is very powerful, very, very powerful, because now if I represent this as, or as a vector using this standard notation, then everything that I set and that we have derived for these vectors applies to functions. Everything, right? So, for example, as above, as we discussed earlier, right? So, for example, I have g is equal to alpha f, right? Or meaning that alpha is a scalar, right? That I can make a function be equal to another function times a scalar, right? So I have the scaling factor, right? Or the scaling property, rather. And I could say h, function h, is equal to f plus g. I have addition. So now a scaling and addition are defined and closed. And therefore, this defines a vector space, right? Same thing. What else? Well, look at this. I can also define the inner product. Okay, the inner product of function or of functions is going to be given by, let's see, now I'm going to define, I'm going to use this notation for the inner product of two functions f and g. Okay, so let's go back. Let's see, make sure I use the exact same notation I gave you the other day. Let's go back to the definition of the inner product that we had here. How did we define this inner product? We said that xy, right, the inner product of xy is equal to the sum over all the elements, right, of xi and yi, complex conjugate, right? Or transpose if I'm in the real domain, right? So now I need to do the same here. So I can do the exact same thing. Can I? Can I just do the same thing? What's that? Right. Because now I'm in the continuous, not the discrete. So instead of using a summing term, I'm going to use the summing term for the continuous, also known as integration. So I'm going to integrate, right, this. So if I can find my notes, I'm going to have f complex conjugate g, right? So far, so good? Now, when I integrate a function, what am I really doing? I'm computing what? The area, or in more dimensions, general, the volume, right? The volume under the curve. So by definition, then, if I do the inner product of a function with itself, this is going to be larger or equal than 0, correct? Cannot be negative. You agree? And when is this inner product be equal to 0? When f is a vector of zeros, right? Excellent. And what happens if f inner product with g is equal to 0? What does this mean? That implies what? What did it imply here? They are orthogonal. Same thing. It means that f and g are orthogonal. Great. So far, so good? Okay. So let's see how we can, oh, I still have space there. So let's see how I can use this to define interesting sets of functions, right? So, of course, if I go all the way back here, right? This set, we know how to define this set for vectors, right? So for example, if I want to define the Euclidean space of p dimensions, how am I going to define this? Well, the first one is going to be 1 for the first entry and 0 everywhere else. Very good, right? In general, E sub I is going to be 0 except for the ith position, right? Which is going to be 1 and then 0 everywhere else. Correct? Yeah? That's for the Euclidean space. And so on, right? I know how to derive or how to come up with basis sets that define vector spaces. Now, how about for functions? I want to find or define rather basis functions that are very useful to me to define any possible function g. Now remember, my goal is to define any possible function g I can have. And for that, I need basis functions. In the same way that here, I wanted to define any possible vector x, and for that, I needed basis vectors, right? Okay. So let's see if we can define a very useful functional set that you're very familiar with this. For this, let's start with just periodic functions. All right, what's a periodic function? Let's give a definition. A function f, let's say f of x, if you will, is called a periodic function if there exists a positive constant let's say, I don't know, capital T, okay? Such that f of x is equal to f of x plus n capital T for all integers n. Okay? So every t steps or time, the function has the exact same value over and over and over and over again, right? So classical examples of this are functions that depend on the angle of the circle or the sphere, right? Or the hypersphere. So for example, the sine of the angle or the cosine of the angle, right? And we've seen this here in this class. So for example, I can have this. All right, great. I have something like that, right? That keeps repeating, where this dimension defines the angle, right? And this defines, anyone? The sine of the angle, right? And let's see, here I have here I have 0 degrees, right? Here at the max I'd have pi halves, and this would be pi, and so on, right? This would be 2 pi, right? 3 pi over 2, so on, right? Okay, so this, you know, I can also write as, if I define here a circle, S1, right? And I have a vector here, then that angle, phi, is what defines this dimension, right? We've already seen this. This one here is obviously the sine. This one here is obviously the cosine, right? Yeah. The cosine is also given by the inner product, right? Divided by the normalization of the vectors, the norm of the two vectors. Okay, that constant t here is called the period, right? Okay. Now, the set of functions that share the same period actually defines a Hilbert space. Right? Okay, so let's use that knowledge to define sets of functions that are going to be very useful to us. So the space of periodic functions that share or have the same period is in fact a Hilbert space. And that Hilbert space is given by, what do we need to define a Hilbert space? We need a vector space. We already have vector space, right? We've shown this. But now we need a norm that is given by an inner product. And my inner product is defined as I integrate f complex conjugate g, right? That's what I had right here. But this is a periodic function with a period t, right? So I need to integrate this from negative t halves to t halves, right? Make sense? Yeah? Now, in some cases, I may have f and g equals 0, in which case the periodic functions are orthogonal. We generally group these functions into families. For example, let's see. For example, I could define a family of exponential functions, right? So maybe let me define the exponential family of I, W, M, T, where I, it's obviously the complex number, the square root of -1. And I don't know, let me call this phi of t. I'm going to use sub m to indicate that subscript here. And so this is the complex number, right? The square root of -1. Wm is equal to 2 pi over t, right? The period t times this subscript, okay? And I'm going to assume m is 0, plus minus 1, plus minus 2, and so on, right? To infinity. So note that this is a family because each element, right? Let's say psi or psi m sub m is going to be equal to e to the power of negative, what do I have? Negative I2 W1T, right? I'm starting here. It goes to negative infinity, but I'm starting at negative 2. So the next one would be -1. So IW1T Then 0, what's going to be the value for 0? 1, very good. And then I'm going to go to positive 1, so I have e to the power of I w1t and e I2 w1t and so on up to infinity, right? And that would be 1. And this is an element of my family. And this set of infinite functions can be used as basis functions. Okay? And in fact, this one is super famous set that you've seen before. What is it called? That's right, the Fourier basis. Very good. So we want to use basis sets like this, and in particular, we are going to use the Fourier basis because the Fourier basis, like this one here, spans the whole space of all possible functions. So with this basis set, I can represent any function I want, right? Well, there's a slight problem that we'll have to deal with when we work with computers, because last time I checked, computers don't have infinite memory or infinite capacity to process infinite computations in a finite number of steps or time. So, okay, we'll have to truncate this somehow, right? And that's when we get into, for audio, we get into, what is it, the compression for audio, forget. Anyone can remember? MP3, very good. And for audio?
Or video?
I'm for video, yes, excuse me. MP4, right? And what's this? It's nothing else than a truncation of the frequencies, right? Because this is Fourier basis to define frequencies, meaning the frequency of the period, right? Frequencies that we either do not hear or we do not see, right? Okay, great. What else? Now, this set in particular, this basis, the set of basis functions that I have here, is actually a set of orthogonal bases. Can we prove that? Let's see if we can prove that. Let's see. Come on, we can do it. All right, so I want to prove that if I have, okay. If I have psi n, psi m, right, that this inner product is equal to 0. Right? That would show that they are orthogonal to one another. Okay, let's see if we can do that. Where do I have the definition of the inner product? Where did I write this? Oh yeah, right here. Gee. Okay, so let's copy this here. So I have to integrate from negative t halves to t halves. The first function, which is equal to the exponential function of negative I n w1t times the second one, which is the exponential of positive now, excuse me, I w m w1t, right? So far so good? Okay. So again, here for now, I'm assuming m is different than n, okay? So I can rewrite this as negative t halves to t halves of the exponential function of I. I'm going to do m minus n, right? Combining these two, w1t dt. And now let's compute that integration. It's pretty much trivial thing. This is equal to 1 over this term right here, I m minus n w1 times the exponential of I m minus n w1t, right? And I need to compute this from t equal to negative 2 half to t halves, right? Okay. So this is going to be, this is the same thing. So I'm going to take this out. I have 1 over I m minus n, this is w1. And now I have this thing, which is the exponential function of I m minus n w1 t, right? Substituting this first one, and minus the exponential function of I and 0, right? Am I right? Yeah, 0. Okay. And this and these are the same thing. So this is equal to, which is this, which is equal to 0, right? That's it, right? Because it's a periodic function, right? Correct? I multiply by t, the period. It's the same thing. Now what happens when m is actually equal to n? In that case, I have phi of m squared, right? Which is the same as, the inner product of this function with itself. And this is equal to, now I integrate again from negative t halves to t half, the exponential of minus I m w1t times the exponential function of I m w1t dt. And what's this equal to? Let's see. This is m minus m is 0. So this is the exponential function of I 0t. Which is equal to integrating from t over 2, negative t over 2 to t over 2, 1 dt. And this is equal to t. Very good. The period. So this shows that for this Fourier basis set that I have here, the value of the norm of each of these elements is equal to the period, meaning I do not depend on m, right? invariant to M. Okay, so with that, I can now say that any function I may want to work with, I can define it in this Fourier space. So I can define this in the Fourier space, right? Any function, excuse me, in the Fourier space by writing that f of t is going to be equal to the sum over all m, right, of my basis functions, which is the exponential function of I, W, M, T times what else? What am I missing here? The coefficients. Very good. My coefficients, right? Cm. And in that case, these are going to be complex scalars, right? Okay. So what's next? What we want to know next is how are we going to compute these coefficients, right? We know how to compute the coefficients for vectors in a vector space. How are we going to compute the coefficients here for this functional space, right? Because if I know these coefficients, now remember that the advantage of knowing the coefficients in a vector space, right, or a tensor space, is that if you have the basis tensors and I have the basis tensors, we agree on which basis tensors we use, then I only need to send you the coefficients. And you can reconstruct any vector, any tensor, right? Here, if I want to reconstruct a function, you have to know the basis functions. I have to know the exact same basis functions. And then we only need to exchange the coefficients, which means I have to be able to compute the coefficients. Okay, so how are we going to do that? So we're going to consider the inner product of an arbitrary function f with the complex exponential family that we've introduced here. And that is, so this is for the coefficients. That is, say, the exponential function of I, W, N, T with f. And what's this equal to? This is the inner product of this, the exponential function of I, W, N, T, with the sum, this f, it's given by this equation right here, right? The sum of Cm times the exponential function of I, W, M, T. Correct? Yes? Okay, so then following from that equation down there, I'm going to take the summation term out. So I have Cm equals the exponential of IWNT, the exponential of IWMT, right? So all I did is I have this thing here, and I take this that does not depend, right, on the other terms. I can take it out, right? All right, and this is equal then to the sum over all m of Cm. Now, what's this going to be equal to? Let's think about this. This is going to be equal to the period t, right? What is that? This here, right? This is going to be equal to that period, right? That we have computed when they are the same. So I'm going to use the Kronecker delta here, m minus n, meaning that when they are the same, this is equal to, and when they're different, 0, which is when m is different than 0, this has to be equal to 0, there it is. And when they are the same, it has to be equal to t, right? Excellent. So this is delta A, it's equal to 1 if A is equal to 0 and 0 elsewhere. And therefore, this is equal to anyone? What's this going to be equal to? Very good, CNT. Excellent, right? And that's obviously the result I want. So now I can take Cn out and define how I'm going to compute the coefficients of any function g, or f, rather. So here, taking, or is it here, Cn out, Cn is going to be equal to 1 over t, right? I'm moving t to the other side, times, what did I have on the other side? Right there, the inner product of the exponential function IWNT with f, my function, right? Yeah. And what's this equal to? This is 1 over t, integrate from negative t halves to t halves of ft, my function, times the exponential function, right? Negative I w n t dt, right? And that is my solution right here, right, for Cn.
So do we need a conjugate on f?
Oh, yes, of course. This is the conjugate here. And these coefficients have a name that's very difficult to remember. They're called the Fourier coefficients. Okay, so more generally, you will see in Fourier analysis, right? You will see this typically stated as f, or f written as a linear combination of the complex exponentials, right? So we have f of t given by 2 pi over t, the sum over all m of f wm, this capital F, the exponential of IWMT, where f of Wm is equal to 1 over 2 pi, the integral of negative 2/2 to 2/2 of f of t, the exponential of negative IWNT dt. Right? And you've seen that many times before, that in Fourier analysis, this is called what? This first part? No one? The synthesis, right? And anyone knows the second part? The analysis, very good. And this f here is called the Fourier transform. Now you'll see the Fourier transform sometimes written as this f of w, right? Or some variation thereafter. They all mean the same thing. And the inverse of the Fourier transform, you may see it as f inverse of capital F now w, right? I remember that when we started talking about this topic, maybe a couple lectures back, 2 or 3 lectures back, we started discussing, started defining linear filters, right? So we're going to be very broad at the beginning, and then we'll get more formal, right? And the very first thing that we defined was the convolution. Remember the convolution, right? That means that you multiply a window, right, onto a larger size image or window, right? And you multiply this at every possible location, and then you sum all over these results, right? What does this mean if I now apply this Fourier transform to my original functions? It means that I'm now doing the multiplication and addition, right, that I had before in the convolution, intrinsically defined already here, right? So in fact, multiplying in the Fourier space is the same as doing a convolution in the original space, right? So if you want to implement convolutions in images, right, like in probably a homework to come, that you need to say, use some of these filters that we define, right, like the derivative of Gaussians, for example, to find edges in images. Now you can do a convolution of that filter with the image, right? Or you can convert these two functions in the Fourier domain and do a simple multiplication and then apply the inverse function, inverse of the Fourier function, to go back to the original domain, and you're done. And what would you rather do? A multiplication or a convolution? I mean, duh, right? I mean, one thing in a computer is going to go like that. The other is going to take forever, right? Now, in a small project, homework, because you don't care, right? You can let it run for a few minutes or a few hours if you have to do a lot of images, and you're done. But in practice, that's not what you want. You want things to work as fast as possible, right? And obviously, the Fourier domain allows us to do that very rapidly, very efficiently. Okay, so let's maybe get a little bit in more details on the Fourier domain, or the Fourier transform rather, and then we are going to move to the discrete version, right? Because computers are still discrete. Okay. So according to what we have derived here, we can say that there is a set of scalars, f tm, let's say, that can, right, these ones that we have defined here, okay, that can synthesize a function capital Fw having a finite extension omega. Okay, so capital Fw, let me define it as 1 over omega, the sum over all m of f of tm, the exponential of negative I tm w, right? That's my synthesis, same as I had defined over here, with where f dm, same as I had defined down here now, is equal to integrating from negative omega halves to omega halves, capital Fw times the exponential of I tm w dw. And let's say that we define as before, tm we're going to set to 2 pi over omega times m. Okay, and now this already allows us to apply this two transformations to images, right? Except for the caveat that images are of finite domain, right? So we wish to apply the Fourier transform, let's call it ft, to images. Now the image is nothing else than a function, right? Only that it's truncated. And what I'm going to do now is I'm going to extend that finite domain to an infinite domain. And to do so, I'm going to make it periodic so I can apply everything that I've done. And how can I do this? By repeating the image over and over and over and over again, right? Perfect. So we assume the function, meaning the image, repeats itself i.e. it's periodic. Okay, now the next thing that we need to do is we also need to assume or to fix, if you will, the Fourier coefficients to, or we need to assume, that's better, to assume that the Fourier coefficients are also finite. Okay. Now the first one we can do directly. That is given, so that we already have. Okay. That we already have, because all we need to assume is that we repeat the image over and over and over and over and over again, right? But this one means that we have to truncate the functions, the basis functions that we use. And to do that, we're going to discretize our Fourier transform into what is called the discrete Fourier transform. Or most typically called the DFT, right? All right, I'll do that next week, and I'll also then we'll use we'll give a very particular description of the DFT, which is the discrete cosine transform, because the cosine can expand also the whole space. Okay, and that is one of the most useful ways of describing functions. That we have, one of them. And in particular, for example, this is used for JPEG. In JPEG compression, use a discrete cosine transform, okay, to describe images. So we're going to see how we can use this technique. There's also, I'm going to briefly talk about this. There's also an extension of the algorithms that we saw in a structure from motion, right? Remember the algorithms that we derived for structure from motion? And I said, we're going to assume in a structure from motion that the objects that I have are rigid objects. And the reason we assume that the object is rigid is because if we assume that the object can deform, then the number of parameters that needs to be estimated is larger than the number of equations. So the problem is under constraint, and there are infinite solutions. We cannot solve it. Well, guess what? We can now, with the discrete Fourier transform, in fact, with the discrete cosine transform in particular, we can truncate the number of parameters that we have, because a deformable object defines a function, right? Functional moment, or a moment that can be defined as a function. And we can define this function in a functional space given by this basis set, right? The cosine set in the Fourier basis set. And by that, I truncate, say, okay, you know, these low frequencies and these high frequencies I don't care about. I only care about these middle frequencies. And now the number of parameters I need to estimate is manageable. And then I can solve for deformable objects as well. And I can extend my structure from motion algorithms that you already know to work for non-rigid objects. Spectacular, right? All right, so we'll see all this next week. I'll see you then.